In this video, we will discuss about the dielectric boundary conditions and dielectric conductor boundary conditions. So, in case of dielectric boundary conditions, you can see this is the medium 1, it is medium 2. Medium 1 is having the dielectric constant epsilon r1, and medium 2 is having the dielectric constant epsilon r2. And this is the normal to the boundary. This is the boundary which is separating the two media, 1 and 2. In medium 1, we are representing electric field E1 bar. In medium 2, we are representing electric field E2 bar. So whenever this E1 bar is entering into the medium 2, it is bending and traveling. So that this theta 2 is different from the theta 1. This itself is bending nature of the electric fields. So, and E1 bar is making the angle of theta 1 with the normal. E2 bar is making the angle theta 2 with the normal. Then this E1 bar can be split into two parts. One is tangential component, second one is the normal component. This tangential and normal components are defined with respect to boundary. You can observe here. E1 bar can be split into ET1 bar and EN1 bar. So this entire E1 bar from the vector addition, we can write the addition of these two vectors. That is what this one. E1 bar is equal to ET1 into T cap plus En1 into N cap. Here T cap and N cap are two unit vectors. Similarly, E2 bar can be split into two vectors. So E2 bar is the vector addition of these two vectors. E2 bar is equal to ET2 into T cap plus En2 into N cap. So T1 or T2 are representing the tangential things with respect to boundaries. And N1 and N2 are representing the normal components with respect to boundaries. Okay. So here what you need to understand means the tangential component and normal component are given with respect to boundary. Theta 1, theta 2 are defined with respect to normal. These are the basic things you have to understand. Then by the application of two equations like line integral of E bar dot dl bar is equal to 0 and closure surface integral of d bar dot ds bar is equal to q. By the application of these two equations, we'll get tangential. These boundary conditions are ET2 minus ET1, and here dN2 minus dN1 is equal to rho s. I'm not going to do those proofs here. This time I'm giving the outline. So ET2 is equal to ET1. This is the one of the boundary conditions, and second boundary condition is dN2 minus dN1 is equal to rho s. So what is the meaning of this one? Tangential components are always same in two media, but the normal components of the electric flux densities are discontinuous by rho s. In some cases, you can take rho s is equal to 0. At that time, normal components of the electric flux densities are continuous in nature. That means those are same. Okay. Now, if the situation is a dielectric and conductor, then what we have? So, this is the boundary. This is normal to the boundary. This medium 1, it is medium 2 having epsilon r1, epsilon r2 as the dielectric constants or relative permittivities. Okay. So I'm taking this medium 1 is conductor and medium 2 is a dielectric. Because the medium 1 is a conductor, here there is no charge, or simply there is no electric field. Electric field is equal to 0 in the conductor. Already we know that one. That means because it is represented as this 1 medium 1, we can tell ET1 is equal to 0, En1 is equal to 0. This itself is E1 bar is equal to 0. Then dt1 is equal to 0, dn1 is equal to 0. This itself is d1 bar is equal to 0. Okay. Then But according to the dielectric boundary conditions, so that is the general case that can be applicable for anything. Now this dielectric conductor boundary is the subcase of the previous one. So anyhow, normal these tangential components of the electric fields must be same. That means here you can have ET2, you need to talk about ET2, EN2 and DT2, DN2. Like this you need to discuss. Okay. So, and we can give DT2 is equal to epsilon 2 and ET2. Okay. Then dN2 is equal to epsilon 2 into En2. These are the general relations in the electric field and electric flux density. Okay. From this I am writing d bar is equal to epsilon E bar. Because we are working in medium 2, you can take like this. So whatever it may be, according to the boundary conditions, I should make ET1 is equal to ET2. But here ET1 is equal to 0 because it is a conducting medium. So ET2 also should be equal to 0. Okay. So there is no tangential component available in the dielectric medium itself. In the conductor, there is no question of electric field. Here everything is 0. In the conductor, this E1 bar is 0 or D1 bar is 0. Okay. But when you have the boundary which is created because of the dielectric and conducting medium, whenever ET1 is equal to 0, ET2 is also equal to 0. That means in the medium 2, in the electric field will not contain any tangential component. That means only normal component is existing. So En2 is not equal to 0. That means only normal components are available. So normal is defined with respect to boundary. So only you will be having the electric fields which are perpendicular to the boundary. This case you can see in the capacitor action. This is the capacitor plate. This is another capacitor plate. You can take parallel plate like this. Okay. We know that here positive charge is established, here negative charge is established. Okay. How the electric field will be there? Electric field will be perpendicular to the plates. Like this we can take. Okay. The electric field will not be like this. Okay. It is not making it. Okay. Some acute angle with respect to the boundary. It is making 90 degrees with the boundary. So you see here free space is there. Here also free space is there or any dielectric medium. Then here we have any free space. How to apply that particular topic dielectric and conductor boundary means this plate itself is having certain thickness. This plate is having certain thickness. Okay. So this itself is the boundary of the previous case. Okay. Conductor, dielectric. And here this itself is the boundary, that is free space. That means free space is the dielectric medium only. And this is the dielectric. This is the free space and this is the conductor. Okay. So you can able to, it is coming under the second case only. That means dielectric conductor boundary. So electric fields will be perpendicular to the boundary. That means in the medium 2 you will be having only the normal components. In the medium 1 there is no question of the electric field. Electric field is not available. In the medium 2 whatever the electric field is there, that is just normal component. Okay. Now coming to these electric flux densities, because ET2 is 0, DT2 is also equal to 0, and EN2 is available, so DN2 will be available. Okay, it is 0, but it is not equal to 0. That's it. So orally you can consider here 3 topics: dielectric, dielectric free space, dielectric conductor. These two are subcases only. Main thing is this one. So here you can take ET2 is equal to ET1, dN2 minus dN1 is equal to rho s. In case of the second one, same thing you can follow. This ET2 is equal to ET1, dN2 minus dN1 is equal to rho s. But where this dN2 is equal to epsilon naught epsilon R2 En2. Like that you can able to proceed, but because here free space is there for the medium 2, epsilon R2 is equal to 1. Okay, that is what you can able to consider. Now coming to this case, already just now we have seen, if you take it is related to medium 1, or whatever the medium you are considering as the conductor. If it is the medium 1, this is medium 2, E1 bar is equal to 0, D1 bar is equal to 0. In the medium 2, you will be having only normal component. It is not equal to 0. And dN2 is not equal to 0. Okay, so dN2 will become here rho s only. In this case, what is dN2? dN2 minus dN1 should be equal to rho s. This is 0. That means dN2 is equal to rho s itself. Okay. So these are the boundary conditions completely.